Good morning, everybody. First, I'd like to thank Abir and my colleague Chrysler for arranging this opportunity to share some of the works with you people. So it's a pleasure to be here. I'm Puru Loganathan, Senior Payments Advisor from National Highways. So I work in the technical team. So I work both on asphalt payments and concrete payments. So I'm also working on updating the DMRB standards and specification and working on some research projects. So smart motorways and etc. etc. So over the next few minutes, I'm going to be talking about the range of topics here. So first one is the background about the legacy concrete payments, and followed by why do we need concrete payments and some principles about the concrete payments and the types of it and the current problems we're facing. And I'm going to be talking a little bit about the payment to tree ratio and some of the investigation techniques we use for assessing our payments, and followed by some of the treatment options, and followed by the work that we did for the updating of the concrete payment maintenance manual. And I will also talk a little bit about the current research works and the trial works that we're working on. So I think my colleague Michael has talked a bit about this, so I'll just keep it short. So rigid payments do compose about 4% of our SRM. It's either in the form of exposed concrete or maybe having a little bit of asphalt overlaid onto it. And they're all built between 1950s to 1985, so at an average of 50 years old. So the rigid payment that we are talking about, they're almost to the end of the service life or even gone past the service life. The various types of rigid pavement that we are having in our SRM is jointed and reinforced concrete, and we have reinforced concrete, and we have continuously reinforced concrete pavement, and we also have continuously reinforced base material. So the map on the right-hand side shows the extent of the concrete pavement that we do have along the inlet network. So moving on to why do we need the concrete pavements? So concrete pavements are actually good. I like it a lot. It's relatively more durable than flexible pavements. It can be designed according to plus MSI, and concrete pavements are particularly suitable for areas where we expect to have differential ground settlements are expected when we have geotechnical issues. And also we need to say concrete pavements do require only less maintenance over the service life. So that's a big thing for us. And it is relatively less prone to wear and surface distress compared to the asphalt pavements. And also, we need to mention it has improved rolling resistance. It means it's likely to have less CO2 emissions compared to asphalt pavements. So I'm going to talk a little bit about the general principles of concrete pavement. So concrete is, as you may aware, it's a brittle material, and it is quite good in compression, but it is weak in tension. It just cracks when stress exceeds the crustal strength. So this one is about the traffic-related stresses. Not only that, the concrete tends to contract and expand due to thermal changes, and again, it cracks at random places. So what do we do about it? In general design practice, we have a couple of options. You can either have it as reinforced option or unreinforced concrete. So the first one is unreinforced. So what we can do is we can induce the crack at regular interval and seal them at the top. And we need to provide double bars for the load efficiency, and to transfer the load between one slab to the other. So that's your unreinforced concrete. The second option you can have is something called a reinforced option. So basically, we design the concrete crack at regular interval, and we provide reinforcement to keep the cracks to be very narrow. And we still need to provide the double bars for the load transfer. So that's your reinforced concrete option. Types of jointed concrete. So these are quite common that you can see on my side. So first one on the left is unreinforced concrete, and the one on the right is jointed reinforced concrete option. So one of the main difference between the two you can see is the size of the base on the left is about 4 to 6 kilo. That's the typical range that you expect. On the reinforced one, you can expect up to 7 to 20 millimeters of span. So these are a couple of photographs of what they look like on the real time. So on the left-hand side, you will be able to see the joints on the base. So that's your unreinforced. You would expect about 5 to 6 meters. And this one on the right is our jointed reinforced concrete, which you would expect to have 15 plus meters for each of the base. And this one is another different type, which is a continuously reinforced concrete. And you didn't see the joints that often, but you will have a continuously reinforced pavement. So what it means is you would expect to see some transverse cracks at very close to space intervals. The ones you would expect are those are the transverse cracks you would expect to see, and they're going to be very narrow. So that's the idea behind it. So this one you can, this is the current practice, this is our standard, and it's quite effective, I would say, because it can last very long with little maintenance if it's properly looked after. So how is it in terms of, so with that background, so how is it going for our SRN, the strategic road network? To be honest, we are, as Mike discussed, we've gone past most of the payments have gone past the service life. It's 40 plus years old now. And we had this privilege of having less maintenance over the design life. And now it's coming to an end. We have gone past 40 to 50 odd years. So in the last 10 years or so, we only had a little maintenance or even no maintenance in some of the sections. The reason being, it's very expensive to maintain and often outside the regional maintenance budget. So the focus was mostly onto asphalt pavements. So now we are coming to an end. We are in a state of need for maintenance now. And also the other reason is it's very highly disruptive to road users because you need to have an extensive road closures compared to asphalt. So I'm going to be showing some of the concrete pavement deterioration examples. So please bear in mind what I'm showing you here is the pavement which is gone past the service life. This is not something you would see everywhere in our network, but there are some pavements which is failing really bad. So some of the examples are here. So you can expect to see midway cracking. These are all structural defects where you do need to have a proper intervention for it. We have a longitudinal crack on the near side wheel path. And this one is shattered slab. And the other one, these are quite common. You can see them on the joint of the concrete pavement. These are big joint stars. So the likely cause for these things are possibly due to issues with the double bars, corroded double bars, or maybe localized soft spots on the ground on the bearing support. So and on top of it, you do have your traffic and environmental conditions, which could lead into these sort of defects. So the first one, the potential causes for these are again, it's traffic and the environment, and also it could, it's likely to have some loss of localized support. And again, another issue we need to be looking at is potential for drainage issues. Even though it doesn't matter how good your concrete pavement is, if you have issues on the drainage, if you have water seeping into the concrete pavement or even an asphalt, you would still expect to have poor subject conditions that could lead to pavement deterioration eventually. So the other types you could think about are something called slab settlement. So again, you could expect to have maybe a void underneath your concrete pavement, or it could be a drainage issue that could cause these sort of things, and even the double bar issues. There are quite a combination of reasons that could possibly lead into these sort of defects. And this one is compression failure at the joint. Basically, these sort of defects are likely to be on jointed pavements, particularly on hot weather conditions that are when the concrete trying to expand due to the defective joints, if it's a locked joint or even there is not enough room for the concrete to expand. So what it tends to happen is it kind of comes up as a blow up, as an inverted V. So this is actually a safety critical defect. So the repair that we are looking at is actually talked about with some asphalt mainly for emergency reasons, but that's not the proper repair rate. So it has to be followed up with treatment option. And the next one is unique to reinforced concrete pavement. So as I mentioned, it's for something related to the continuously reinforced concrete pavement. These are called punch outs, where you would expect to see some of the closely spaced transverse cracks. When they tend to connect with other longitudinal cracks, you can expect to have defects like this. These are punch outs. At some point, it will even be safety critical. So that need to be dealt properly. And apart from the structural ones, there are also other defects. These ones are very minor and surface defects. So you can expect to have surface pop-outs, crazings, and the other one is finished joint seals and some shallow spalling. So there are lots of different reasons to it. For the crazing, for example, if you are having early bleeding in your concrete mix, and the poor activity or even curing issues, those can contribute both for surface pop-out and glazing. And for perished joint sealant, it's mainly the age of the sealant material. If it's not replaced quite often, and that could lead into issues. So shallow spalling is mainly a superficial defect. Now I would like to talk a little bit about the investigation techniques. Michael has discussed quite a lot about the advanced end-to-end digital, but these are very basic points that we normally use for investigating our concrete asset. So the one on the left is visual conditions survey, which is carried out on a traffic speed, which means we can bring ultra high precision photographs of your network. So which is correspond to your map. You should be able to see where you are exactly on the map. And it also comes along with another feature of GPR, which is ground penetration radar. So that basically the map here, you see the relative thickness of different layers of the pavement. So it's quite easy to get the condition of your pavement while using the traffic speed of the automated vehicle. The one on the right-hand top corner is the usual old school technique. We do have a core sample just to understand what is the material, the thickness of it, what sort of defects we are looking into. So that gives you kind of information. The one on the bottom left is called falling white diffractometer. We use it widely on asphalt, both asphalt and concrete. For concrete, mainly we use it for understanding the load transfer efficiency between the deep slabs. So once you have a joint in between, it's important to understand how exactly we are actually transferring the work from one slab to the other. Because of the driver issues or even some loss of support could lead into poor load transfer, which means each of the base gets isolated in the start to be traded quite faster. The one on the right and bottom corner is actually something called the lightweight diffractometer. Once you've taken a core out of it, then you can use the basic core code to use this lightweight diffractometer just to understand the condition of the sunlight. It gives you about the surface sunlight modulus. Then you will get an indication of the strength of your foundation. So, with all sorts of the investigation techniques, it's quite important to work out the root cause for individual defects. There is no such one-off treatment that can fit everything. So it's really important to work out what is the root cause for each of those defects. Then you need to come up with a maintenance strategy. So now I would like to talk a little bit about the common treatment options. Again, so for treatment options, the first one on the left-hand corner, it's inlet crack repair systems. For example, if you have a crack, you could think about inlet crack repair systems, which is basically you are getting an emulsion, and that's one of the systems that you can easily use on. And the one on the second one is basically using a calcined bauxite on top of that emulsion that we put on. It's mainly to improve the speed resistance for that particular batching. And the one on the right-hand side is a shallow repairs. For example, if you have a very superficial, but you still need to get it done. So you'll be looking at around 20 to 40 mil deep. So that's your shallow thin boundary repairs. The one on the bottom corner, this is for slab stabilization by back and down. So this is mainly for the the scenarios where you have slab settlements, where you found out that you have potential void under your slab. So this is a technique where you can actually can be used to stabilize the slab. So literally you can force the air to create a vacuum, and then they use either a resin-based or cementitious mortar to stabilize the slab. So that's one of the advanced technique we still use. And this one, these are very intensive one. For example, if you think that, for example, the ones we discussed about the shattered slabs or even the mid-play cracking. So those are the scenarios that indicate that the particular slab is, that it couldn't go any further. So those scenarios, you should be looking at some deeper treatment, either a reconstruction or even a bay replacement. This is a bay replacement. So that's the joint that they've excavated through. Then the cycle is actually bringing the blocks into it, and then followed by you have your the fresh concrete laid onto it. So that's your common technique for bay replacement. Just summarize some of this. As part of this legacy concrete program work, we have updated our standards as well. So the link on the top is our specification link. So based on our experience and the research so far, we constantly update our works. So I just summarized for the ease. If you have a surface defect, there are a couple of options within the specification which is recommended. So for surface defects, you can talk about, you can think about thin boundary defects, and for joint seams for finished ones. Structural defects, these are the common ones. So these numbers on the right hand side is actually the class references to that specification 1000 series. I hope that was a useful link for you. Well, followed by that, because the legacy concrete program, as Mike mentioned, is going to be for the next 30 to 40 odd years. So, the last 10 years or so, we never had a proper maintenance strategy for the concrete. So it's going to be a long journey. Then we started to think about how do we do it. Then we came up with a project, something called the Innovations Project. We reached out to the industry and we asked them, because the technology has advanced quite a lot in the last 10, 20 years or so. We haven't done much work on concrete. Then we got up to the industry and we understood about lots of technical advancement in the concrete materials. And we asked them to trial it on our network. We then tried quite a lot of different products. And we also tested a number of different non-destructive testing methods and the different treatment options. And then we, before we actually go into our work, we wanted to update this huge piece of concrete pavement maintenance manual. So this was initially published in the early 90s. Now we managed to update it quite substantially. It's about 300 page document. It covers quite a lot about the concrete if you're interested. It talks about the mechanics of the concrete payments and deterioration, and it talks about lots of advanced investigation techniques and treatment options if you are interested in. So there's a link in it, and if you're interested, you can please feel free to download a copy. It's a free of cost for you. So I want to now talk about the research and trial works that I'm personally working on and as part of the team. So this first one is actually the project that I'm working with Professor Abir, which is on low carbon concrete with the self-healing properties. So self-healing is something that's been explored quite a bit for the structure side. It's been tried for concrete to some extent, but it hasn't been tried for concrete payments. So the idea is we wanted to, from the project, we wanted to understand what are the different self-healing options we have and how do they interact when it comes to concrete payments. So, for example, you could have capsules or even fiber reinforcement, mineral additives, or the SAP, the super absorbent bodies. The fourth one is my kind of favorite because it kind of absorbs moisture and it tends to expand, which is kind of possibly a healing option for minor cracks. This the outcome from this research, I'm not expecting it to be a huge rehabilitation option. It's going to be more of a first time for initial cracks within the concrete. So That's one of the work. The second one, this is with working along with Nottingham University. So this is mainly for drafting out the declaration model for the concrete payments. So because the declaration model will definitely guide us in terms of, because it's our network is huge and we have lots of different schemes for different regions. So we wanted to prioritize where we want the spending to be. So the declaration model, hopefully the outcome will give us a guidelines of where to prioritize our investments. So this work is expected to cover both the exposed to concrete as well as the deeper concrete sections we have on the network. Well, that's the last one which I was doing this last week. As we all know, the concrete is quite noisy and it's, sometimes it's very unpleasant for the road users. So there are a number of different techniques that are coming through. We already have something in place, but this one is a new technique. It's been tried in states before, so we wanted to try it on the UK road. So what it is basically you have a concrete road here. This one we are trying to do a longitudinal grooving, like these trucks and channels, using diamond blade preparation. So what it does is it kind of draws this the machine to get a grooves and channels like that. So basically what it does, it's improving the skid resistance, and also it's relatively quiet compared to the central concrete road. So yeah, it's still at the early stages, and I found it to be very interesting, and if it can help reducing the noise, so it's something we would like to explore further on. So this is one of something one. So that was the recent work. Yeah, that's about really. So just to giving you a flavor of what we do. So I'm more than happy to take any questions.
What's the maximum crack width for the concrete house? If it's disturbed,
if it's a reinforced concrete pavement, those cracks are you would be expecting less than 0.5 millimeters. So anything more than that, you need to.
And if you use the healing technology, the healing agents could close the crack partially or.
The healing, it's still at the early stages. Even I'm new to the concept, but I can answer to this. So the healing, we're not expecting to bridge the whole gap of the crack, but it can act as more of a first step. For example, early shrinkage cracking, or even, I wouldn't expect to go more than 1 millimeter. Please, Adirish, correct me if I'm wrong. So that's the sort of practice.
So if it happens, you have a higher percentage of CO2. So how you can control the carbonation?
Sorry, sir.
I mean, if you use the healing agent to heal the crack partially, not total, you still have a high percentage of CO2, and definitely carbon. There is the carbonation will start soon.
I mean, carbonation is from your atmospheric carbon dioxide, but strictly speaking, carbonation is good for concrete if you don't have reinforcement. So yes. Because of the carbonation, we tend to have high carbonate, which actually reducing the concrete strength as well. But in general, CO2 emissions are a problem for concrete. So what we're trying to do is we have a couple of options. Because we have so much of this asset here, we could either go for a complete reconstruction or life extension. So we are working on both of these. So I do accept concrete does have, in terms of CO2 emissions, we have contribution. But that's the reason we are trying to explore a little bit about low carbon concrete. So instead of having 100% same one, we have some industrial activities like personal to reduce the cement content. So thereby you are actually reducing the CO2. So that's the
thank you for your presentation. I actually had a question about your previous slides. So the longitudinal roofs that you put in to reduce the noise, how does it work with regards to the evacuation of water? Let's say it rains. Does the rain not stay in these roofs and thereby
Yeah,
change
these
the
are, you mean during the process or during the service?
No, after, let's say the road is in use and there is a heavy rainfall, does then the rain not stay in these roofs?
Not really, because once you have these channels are about 5 millimeters, less than 5 millimeters. Once they're not, you won't expect to see water ponding on the surface. That's the idea. Once you have a moving vehicle, it will be going towards the drainage path. So you will have a little bit of camber in there. And I don't expect to see too much of water ponding. We currently have a technique which is slightly, the span is thinner than this, and that's one of the valid questions. We still need to see how this is going to happen. But our idea is it's going to be so small, and with the traffic movement, you won't expect to see too much of water ponding. Anything from the chat?
Yeah, there is no questions from the chat. So thank you
Thank
for
you.
your nice presentation.
Thank you.
Yeah.
Thank you.
Thank you.